Good morning, everyone. My name is Michele Lacerenza from Politecnico di Milano in Italy, from the Applied Physics department. Today I'm going to talk to you about our latest project that is about functional brain monitoring of freely walking subjects using time domain NIRS. I have to disclose that I'm co-founder of Pioneers, a recent spin-off from our university, and we are developing the new generation of time domain NIRS oximeters. This is the outline of my presentation. I will briefly talk about time domain NIRS, an introduction. Then I'll show you the device that we use for our measurements, and we will go through the in vivo experiment concerning walking freely moving protocols and drawing the conclusions at the end. Talking about time domain NIRS, this is a technique that uses near infrared light that is pulsed, and it is injected inside the tissue with pulses that are very short in time, hundreds of picoseconds, and thanks to the diffusion and the absorption inside the tissue, it is possible to retrieve the optical important coefficients such as absorption and scattering coefficients. Thanks to this information, it is then possible to retrieve and estimate the concentration of deoxygenated hemoglobin and saturation and total hemoglobin of the tissue under study. Other than that, a added feature and intrinsic of this technique is the possibility to disentangle the information from upper and lower layer of the scanned tissue. So the photons coming earlier in time, so looking at the pulse that is arriving at the detector, are bringing information coming from the shallow layer of the brain under study, and photons coming later in time are bringing the information about the cortex, so functional information. So when we talk about functional information, we are expecting activation of the cortex, in our case the motor cortex, due to a exercise related to motion. This is why we have to talk about a hemodynamic response function, that is a function that models the activation inside our brain. We took a particular model depicted in the paper by Yuga et al. That concerns the combination of two gamma function, as you see in the pictures, and four main variables, tau p, a, tau d, and b. A is the amplitude of the first gamma function, b is related to the amplitude of the second gamma function, and then we have the two delays of the two peaks. This function is then convolved with the boxcar function that gives information of the stimulus time. So once we have the raw data retrieved from our experiment, such as the one on the bottom left, that simulates the activation of our tissue. So when an activation occurs, the oxygenated hemoglobin increases its concentration during the task, and the deoxygenated hemoglobin decreases. In this case, we have oxyhemoglobin as an example. So after the convolution with the boxcar function, we have to use a fitting procedure, in our case the least squared, with two of the two variables. We fix the other two for simplicity. And after the fitting process, we have a guess of the final hemodynamic response function for the activation here presented. On the right, we have the equations needed, and on the bottom, we have an example of 5 different experiments, of 5 different repetition of the same experiment, where we have the 5 activation: oxyhemoglobin on the top and deoxy on the bottom. As you see, oxy is increasing and deoxy is decreasing during the task. So continuous wave NIRS, compared to time domain NIRS, have many pros. So it is very compact, and it is not expensive at all compared to the time domain NIRS. So what we are doing at Politecnico di Milano is trying to bring in some of the pros also to time domain NIRS. So, because nowadays time domain NIRS systems that use pulsed lights, continuous wave NIRS use just LEDs or laser continuous lights. I would say in time domain NIRS systems are very bulky nowadays, comparable to big fridges. So people usually don't wear them, but they lie on them during the measurements or at the hospitals. So what we came up with is the NIRS box at Politecnico di Milano. We developed this system in collaboration with the electronic department, making all the components smaller and shrinking all the dimensions. The system is composed by the components here depicted. We have custom-made pulse laser, custom-made electronics and optics, and we also developed a silicon photomultiplier module. Then we have a time-to-digital converter developed by the electronic department as well. And you have the scheme of the system on the top right. You can stop the video and look at it for a deeper understanding. So the NIRS box system is this one on the right, and it can be weared as a backpack. It has 6 hours of autonomous lifetime, and it can be controlled wirelessly by phone or by laptop. It is all automated, and it is rugged. I'm going to talk to you about this particular protocol, the working protocol that we perform on 3 different subjects. We ask the subject to stay at rest for 20 seconds, acquiring the baseline, then working forward for 20 seconds and recovery for 40 seconds, and repeat this task 5 times on a row. And then making all the protocol in case of forward walking on a straight line, then all of it again in backward walking, also on a straight line with eyes wide open, and standstill condition. That was the control. So we asked the subject to stand still, to not move, but we kept giving them signal, start and stop signal for the task. The probe was placed on C1 position from inside the motor cortex area, following the EEG 1020 system. Those are results from one subject. The other subjects are very similar. And as you can see, we don't have any activation in case of the control condition where no movement have been done by the subject. Then we have a clear activation for nearly all of the repetition in case of forward walking, the second row, and we have substantial activation for each of the tasks in case of backward walking, suggesting a major involvement in case of backward walking of the motor cortex compared to the forward walking. We're writing a paper about this project, and it is under submission. So after that, we decided to group all the subjects and all the repetition and make an average for each of the tasks. So we have the control standstill task, then the forward walking task, and the backward walking task on the columns here reported. And we have the analysis of the extracerebral layer, the upper layer of the brain, and we have the information of the lower layers or the brain cortex of all the subjects. And as we can see, in average, we don't have any motion artifacts on the upper layer or systemic variations. or hemodynamic systemic variations, and we just have flat lines for oxy and deoxyhemoglobin. And for what concerns the lower layer, as expected, we don't have any activation in the standstill task, and we have clear activation forward and backward walking. It is interesting to notice that the hemodynamic response function adaptation, so the adaptive hemodynamic response functions, is working well in case of oxyhemoglobin, while it has to be improved for the deoxyhemoglobin. As you can see, the first raising edge of the activation in case of the deoxyhemoglobin is not followed well, but is only the dropping edge is followed. So it will result in a later deoxyhemoglobin activation. As conclusions, we developed a high-performance device with very interesting features, being portable and compact with low sensitivity to motion artifacts. We managed to make the first in vivo experiment with freely walking subjects, and we applied the adaptive hemodynamic response function algorithm and its analysis on the average of the subjects and repetitions. We are hoping in the near future to open new frontiers in 3D moving measurements in more ecological conditions for the subjects, and we are getting ready for clinical trials. I thank all of you for your attention, and I'm open to any question.